Hi, my name is Davi Cavinatto. I'm an undergraduate researcher at Brigham Young University. Today I will be talking about a project that we have been developing in the past year and a half. A little bit of background. At around the turn of the century, a group of Canadian researchers were exploring a new type of technology. They had made a small MRI gradient coil that was built around an imaging cavity containing a guard gel. An ultrasound transducer was placed by the cavity and was used to create a 500 kHz wave in the cavity. The gradient coil created by these researchers was given electrical current at the same frequency as the ultrasound transducer. This apparatus, through the spatial gradient of the magnetic field generated, would encode ultrasonic vibrations into the complex phase of an MR image, making it possible to visualize the small particle motion created in the ultrasound field. This created a new method in the field of ultrasound exposimetry that now allowed direct measurement of ultrasound properties without the old constraints of material transparency and homogeneity. We at Brigham Young University, seeing how incredibly useful this non-invasive ultrasound visualization technique can be, started developing a motion encoding coil that can be used not only inside a small imaging cavity, but outside the volume constraints of the last design. Our new design could provide ample apparatus versatility, allowing the technique to be applied to human tissue that was previously inaccessible, such as the human brain. This novel approach could be used to establish the missing correlation between the results of neuromodulation treatments and their mechanism of action, thus improving the scientific rigor of this field of research. In order to make this new application work, we needed to develop a motion encoding coil that is optimized for maximum magnetic field spatial gradient. In the past papers, it was noted that a 0.4 Tesla per meter gradient at the visualization cavity was enough to grant an image of SNR of 10. Using those numeric constraints, as well as the electrical current and power needed for the past design, we started developing a single coil design that would at least match the same gradient values of the last research while also making the design versatile. Knowing that the maximum gradient possible in the longitudinal direction would be generated by a single turn coil of infinitesimal wire diameter, we started to investigate ways of making a design that would approximate that expectation while conforming to our other constraints. By analytical and numeric simulations using software such as COMSOL Multiphysics, FEM, and Wolfram's Mathematica, we found that a 36-turn single coil of outer diameter 40 mm, inner diameter 20 mm would match our gradient requirements for this design. Since the coil is to be driven by a 500 kHz sine wave, we opted to use Litz wire that matches the skin depth of copper at that frequency and reduces the skin effect caused by the high frequency current in the wire. This optimized motion encoding coil was then placed in an LC resonant series circuit, which was then used to effectively cancel the imaginary resistance of the coil while creating a pure 500 kHz sine wave. This electrical circuit, thus optimized for very low electrical resistance, was impedance matched and tested with an RF amplifier at the expected resonant frequency. This showed us that our earlier expectations of power dissipation and magnetic field gradient were accurate. Driving a 20 amps 500 kHz sine wave across our coil led to a minimum simulated magnetic gradient of 0.4 Tesla per meter at the target distance, which we had established it to be 2 centimeters. This distance was chosen due to the minimum distance between the coil and the cerebral cortex in order to obtain good quality images of the ultrasound field as it propagates in the brain. The in silico design of the motion encoding coil has proved to match our expectations of spatial gradient at the target region. The thermal losses were small, thus showing that the current model can be easily used in much higher values of electrical current, producing even more magnetic gradient and improving imaging volume size, and image SNR. In the following months, we will implement an MRI triggering system in order to obtain the first images made possible by our coil prototype. Part of this project was paid by the Focus Ultrasound Foundation and by the National Science Foundation. I'm now available for questions. Thank you.